Today we'll be talking about phase difference. So before that, let's try to look at this water droplet experiment again, where the waves on this water are traveling away from the source of the droplets. So I place this water level measuring device. I just call it oscilloscope for simpler reference. Yeah. So this oscilloscope has two readout. Okay, I actually have placed them together at this position here. Okay, at this position here, so that you can see on this oscilloscope screen, it has the displacement shown on the screen, going up and down according to the displacement of the water. So what happens if I start to move one of the readout away? Then you can see that they split into two graphs. So this two graph actually showing you the movement of the water molecule at that particular position. Okay, and now you can see that they are crossing each other. So when I place them together, they are the same. Okay, so this kind of situation we call them in phase. Okay, we call them in phase. They have no difference in their parts of the oscillation. So now I'm going to freeze the diagram. Okay, and then I move these two to two identical peaks. Okay, so to two identical peaks, and then I run it again. Okay, so you can also see that basically they have no difference. It's just about their amplitude because it has dissipated some energy. So basically they have no difference. Okay, we call this kind of oscillation again in phase because they overlaps. So if I move it to another position, which is a bit further away, again it's a similar identical peak. So it also show me in phase. Okay, a bit away, but never mind. Okay, the idea is these two water molecules on the wave are actually in phase. Their oscillation are actually in phase. So at other position where I randomly pick, and you can see the graph, they are not overlapped on each other as shown in the oscilloscope screen there. Then we call that kind of situation as out phase. Okay. So now we're going to go into a little bit more detail on the idea of phase difference in terms of some numbers. Okay, so phase difference basically can be expressed in two units. One is called the radian, and the other one is called the degree. So 360 degree, we know that is for one cycle. So in terms of oscillation, is one complete oscillation. And also for radian, in maths you already learned that 2 pi radian is for one circle, right? So in terms of oscillation is one complete oscillation. So 2 pi is one complete oscillation. So if two of the water molecule they are in phase, we can see that their oscillation is like synchronous. Then we say that they have zero phase difference, zero radian phase difference, or 0 degrees phase difference. So we're going to look at another situation where they have half a cycle that they are ahead or behind each other. So to demonstrate that, I'm going to move one of these readout at a peak, and I'm going to move the other one to a trough. Okay, to a trough, its lowest position. Okay, so that they are going to show us the case of half a cycle difference. Half a cycle difference, if you divide by 2 pi, that will be a pi radian. If you divide it using the 360 degrees, then it will be 180 degrees of the phase difference. So you can see the graph crisscross like that. When one is at the peak, the other one is at the trough. When one is at 2 cm at the positive side, the other one will be at the 2 cm on the negative side. So that is half a cycle in terms of their phase difference. So what happens if I now switch to a position where they show us quarter of a cycle in the difference of their oscillation. So quarter of their cycle, I need to use a measuring tape first. So just now it was about, let's say, let's make it 1.4, that will be easier for us. Then 1.4 is this half cycle, right? So half of the half, that will be about 0.7. Okay, 0.7, so I'm 0.6 now. Okay, 0.7 can. So I just move it slightly here as a reference. If not, then I don't know where to put. Okay, so this one will be like quarter of a cycle of this wave. And then we can see that they almost run parallelly. Okay, and then you can see their peak, the two peak on this CRO screen here, they are very close to each other, but they are not really overlap, and they are not like one on peak and one on trough compared to just now. So they are like a parallel wave going together. Okay, so this case is actually quarter of an oscillation. Okay, quarter of an oscillation. And now we're going to go back to the slide. Yeah. Okay, so referring back to the PhET simulation just now, where I have the case of 2 points oscillating in phase. So this is like point A and B on the wave just now. So when we plot them against a graph of displacement against time, they should show us a similar pattern, that each of the point here, they are tally with each other. When one is 0, the other one is 0. When one is trough, the other one is trough. When one is peak, the other one is peak. So again, this kind of case is called the in phase. Okay, so it's called in phase. Okay, while the other one, we have point A and C. So I skip the part where A and a point, let's say D, they are 180 degree or half a cycle out of phase. So I straight away go to this idea of the quarter of an oscillation. Okay, quarter of an oscillation, let's say point C. So again, it's a case where they are out of phase. So now let's look at it in slightly more details. Phase difference, as I mentioned just now, is a fraction of a cycle where one particle moves ahead or behind each other. So the two graphs in the earlier slide, now I overlap them on the same axis. And then from here we can see it is similar to the one that we did on the PhET simulation just now. So point A and point C, they are displacement time graph. We put them together. Alright. So now we want to calculate the phase difference. So the process of it, putting it in terms of mathematical quantities and terms, that will be theta equals to 2 pi times the t divided by the period. Okay, so this t here, this theta here, it represents the phase difference. Okay, and then sometimes we write delta theta also. And then this t actually is the difference in their timing. The difference in their timing. Okay, so I have placed 4 lines here, actually 5 lines, to let us see what is their difference in their timing here. Okay, so first of all, we are going to find 2 points that we're going to use as a reference. So let's say the 2 peaks here. This peak of point C and this peak of point A. Okay, oscillation of point A and point C. So I pick their particular position, which is the peak next to each other. So we can see that the difference in the timing here is t is like quarter out of the whole period here. So this is the whole period. Okay, and that's like a quarter of it, right? And therefore it will be 1/4. It's quarter of the period, so it's like t over 4 divided by t, so it's 1/4. Therefore when we times 2 pi, then you get pi over 2 radian. You get pi over 2 radian. Okay, so in terms of the degree, like I mentioned just now, another way of measuring the phase difference, that will be 360 divided by 4. Okay, so now we come to this part where we have again some points along the string. Okay, some points along the string, just like points along the water waves just now. All right, so we have P, Q, R, and S, and we are going to identify their phase difference. So the difference now is that we don't have the CRO to help us see their pattern of this oscillation of the points. Okay, remember the FAT simulation just now. We have a CRO screen showing their individual displacement and overlap on the same time axis, right? So if we don't have that, then we have to use another method. Okay, so I have to, hold on, I need to make some adjustments first. All right, what we need to do now is we need to use back the same idea just now, that it is related to period and also the difference in the timing, right? So now we don't have the CRO to show us the oscillation, so we use the graph itself, okay, to find a wavelength. Okay, we know that between P and the S is one wavelength because it's between two peaks, right? And then further on we divide the graph into 4 sections, like what we did for the time just now. So this one is distance is x, so we can do the same thing. So now we have 4 sections here, each part of that is quarter of the wavelength. And if we are talking about in terms of the P, Q, R, and S, then we can actually start to find out that between the P and R, this is showing you the P and R, the phase difference between P and R, so basically is x over lambda, right? Therefore the P and R, they are actually half, the difference is actually half of lambda. So between P and R, that's the x here, is actually half of the lambda. So that's why it becomes 2 pi times half, it become pi radian. So now if I ask you what is the phase difference between R and S, okay, phase difference between R and S, okay, so that's number 2. Number 1 we have figured out, and phase difference between P and Q, and phase difference between Q and S. So if I ask you this, can you figure out the phase difference in terms of radian? The phase difference in terms of radian. So that will be your assignment, yeah? Okay, I'll see you in the next video.